Okay, good day. So, welcome to our video lecture series. So, we're going to discuss about numerical differentiation. So, first method for numerical differentiation. So, actually, ano to eh, this lesson combines numerical integration and numerical differentiation. So, dapat mauna muna integration. But, sa itong syllabus ng numerical differentiation, so let me first discuss the numerical differentiation. So first method is the high accuracy differentiation formulas, which is based from Taylor series expansion. Okay, we'll have some review about Taylor series. So from previous lesson, lesson 2.1, we already discussed the Taylor series expansion. So there's the Taylor's Turing box, box 4.1. If you will remember the Taylor's theorem. So this Taylor's theorem. So make sure to review this Taylor's theorem that we'll be using for numerical differentiation and numerical integration. So please take note of derivative or Lagrange form of the remainder. Okay. So technically, we use Taylor series to predict a function value at one point in terms of the function value and its derivatives at another point. In particular, the theorem states that any smooth function can be approximated as a polynomial. Okay, eyes on the screen. So with the difference, so it can be represented generally as f of prime of xi, or the xi is the points in the axis that you want to find the uh, derivatives. That is f of x of I plus 1 minus f of x of I divided by x of I plus 1 minus x of I plus O, x of I plus 1 minus x of y. So where the change of f of I is referred to as the first forward difference, and h is called the step size. Okay, so ito. So this x of I is the any point sa atong function. So this is functions, or this is the graph of the functions. So this is the point where we want to get the derivative. So you have next step size of 1. So not plus 1 ka. So forward. And you want to get the derivative of this area. Okay. Then, forward siya kasi from x of I, or sa initial, kung asan mo gustong hanapin yung value, nag-forward ka. Forward. Okay. Pagpabalik, from original to previous, that would be backwards. So, x of I plus 1 minus x of I, so that would be equals to h. So, ito yon, yung change na to. Then this is the function of x of I. At this point, this is the function of x of I plus 1. Okay, so implementing the Taylor series expansion para sa forward numerical differentiation. So ito yon ang mangyayari. So ang nangyari, difference or change in the function of x of I. So f of x of I plus 1 minus x of I. Yung may mga plus 1 na yan yung mga step size lang divided by the h. So ito yung h. Itong difference ng dalawa. Then plus the order O. O kasi order of error. Pero yung error kasi na yon is equivalent to x of I plus 1 minus hi or the remainder. So that's the length of the interval, but with approximate is made. And for the backward, so ganun din yun. So sa backward naman, ganun din siya. So using this Taylor series expansion, ganito ang mangyayari. Since pabaliktad, ikaw ng minus the first derivative function of x of I plus h plus f of double prime x of I divided by 2 factorial. So ganun yung Taylor series natin. So ganun din yan gagawin sa sa forward. So bali ito kasi first forward difference. So kasama pa ibang term like hanggang sa fourth derivative, fifth derivative. So dadami pa siya. Okay? Then let's go to centered. So centered approximation of the first derivative naman, this is the third way to approximate the first derivative, is to subtract the equations from the backward function. So ito yun. So ito, i-minus mo dun sa backward dito. And you will get these functions to it. So that is called centered. Okay, so we have here the first derivative as may second derivative na siya or may second term, third term, fourth, and so on. Okay, so it has two versions, the first and the second version. So the latter version though is incorporate more terms of the Taylor series expansion and is consequently more accurate. Okay. Next method is Richardson extrapolation. So it is used to two derivative estimates to compute a third, more accurate approximation. So it provides a means to obtain an improved integral estimate I. Itong formula na to is na-derive sa numerical integration. So hindi pa natin na-discuss. So it is where I, h of 1 and I, h of 2 are integral estimates using two step sizes, h1 and h2. So because of its convenience when expressed as a computer algorithm, this formula is usually written for the case where h2 is equal to h1 divided by 2. So as in the integral is equal to 4/3 I h times multiplied by h2 minus 1/3 of I multiplied by h1. So in similar fashion, it can be written for derivative as. So imbis na I, gagawin lang natin siyang derivatives d. So for centered difference approximation with ordered h of squared, the application of this formula will yield a new derivative estimate of OH of 4. So, okay. So next approximation or method, we have derivatives of an equally spaced data. So itong first two method is for equally spaced data. Ano ba ibig sabihin nun? Kunwari, itong space ng dalawa, halos parehas lang. Pag unequally spaced, hindi parehas. It's either this point, ang x of I minus 1 mo or x of I plus 2 mo, hindi sila pare-parehas ng width or ng change in h. So may mga data from experiments or field studies is often collected at unequal intervals, so hindi pare-parehas. So such information can be analyzed by fitting a second order Lagrange interpolating polynomial to its set of three adjacent points. So the second order polynomial can be differentiated analytically to give f of prime of x is equal to f of x minus 1, 2x minus x1 minus x of y plus 1. So ito na yung magiging formula. So where x is the value at which you want to estimate the derivative. Okay. Although this equation is certainly more complicated than the first derivative approximation, it has some more important advantages. So uno daw, it can be used to estimate the derivative anywhere within the range prescribed by the 3 points. So if you want to estimate any points, kahit saan daw, so ito yung the best na method na pwede mong gamitin. Second, the points themselves do not have to be equally spaced, so yun nga, unequal. And third, the derivative estimate is of the same accuracy as the centered difference. Yung level of accuracy, same sa centered difference. Next, for partial derivative, another method where are computed some as ordinary derivatives. So for equally spaced data, the partial first derivatives can be approximated with centered differences. Suppose that we want to determine the partial derivatives for a two-dimensional function, the x and y functions. So for equally spaced data, the partial first derivatives can be approximated with centered differences using this equation. Okay, partial derivative of f with respect to partial derivative of x. So ito, then after which kukuha nyo rin yung partial derivatives of a function with respect to y. Okay. So for higher order derivatives, we might want to differentiate a function with respect to two or more different variables. So the result is called a mixed partial derivatives. So if we want to take the partial derivative of function xy with respect to both independent variables, so we can get use this formula. Double derivative of the functions. To develop a finite difference approximation, we can first form a difference in x of the partial derivatives in y. So, ito na yun. Magiging ganito na siya. And then, we use the definite differences to evaluate each of the partials in y. So, if we will evaluate itong mga nakuha natin na values dito or terms. So, haba siya ng haba. And then, collecting terms to yield. Ito na yan, yung final formula. Okay, so we have some short example. Okay, so this is a problem. So we have the functions of f of x is equal to negative 0.1 x raised to the fourth minus 0.15 x cubed minus 0.5 x squared minus 0.25 x plus 1.2, where at x is equals to 5 and h is equals to 0.25. So we will first get the true value of the first derivative of the functions. So f of x, or f of prime of x, so natin kunin yung first derivative, so that is equals to 0.1 times 0.4, so that is equals to negative 0.4 x, 4 minus 1, so raised to cube. Okay, minus 3 times 0.15, that is 0.45 x raised to 3 minus 1, 2, minus 2 times 0.5, 1.0 x raised to 2 minus 1, that is 1, then minus 0.25. Oh, ano nangyari? Okay, for the true value of the f of prime of x, so that is equals to negative 0.4 multiplied by the value of x. X is equals to 0.5. h squared. Okay. To negative 0.4 times x raised to cube minus 0.45 times x raised to square minus 1.0 times x minus 0.25. Okay, so this is the true value of the f of prime of x at point x equals to zero point 0.5. Okay, using the high accuracy differentiation formula, so we have the forward difference of accuracy and the backward difference of accuracy and the center difference of accuracy. So ang gagawin natin, we have the x of 1 or x of I. That is equals to 0.5. Okay. Then we have the h that is equals to 0.25. So x of I minus 1 and x of 2. Ito for the backward, and the forward is 2. Okay, so we have the value of 0.5, so this is equals to this value minus the h is 0.25. Then that is equals to this value minus h. Okay, so this equals to plus 5 0.25. Alright, now we will compute for the value for the f of x. Enter natin. Okay, for the x of I minus 2, so that is equals to negative 0.1 multiplied by the value raised to 4 minus 0.15 multiplied by this value raised to cube minus 0.5 multiplied by x raised to 2 minus 0.25 multiplied by x plus 1.2. So that is equals to 1.2. Okay. Then we will just drag this down to get this value. Alright, now we will compute for the forward difference of accuracy. So input some formula for the forward, is for the backward, and for the centered on the first derivative. So the f of prime for x of I first, that is equals to 0.5. So using forwards, so using this formula, so mas maganda daw tong second formula, that is equals to negative close natin, negative f of x of I plus 2, that is equals to 0.2 that is equals to negative plus 4 x of I plus 1 yeah, ano na, plus 4 times k minus 3 f of x of I times 0.925 k, then divided by 2h, divided by 2 times h is 0.25. Okay, so this is the value for the forward difference of accuracy, and for its error, so that is equals to true value minus the approximated value divided by true value times 100. So it gives us a percent of 5.82%. All right, for the backward difference of accuracy, so using this second formula, so that is equals to 3 times f of x of I minus 4 times f of a minus 1, so this is the value, plus f of x of 1, so yan. Okay, then divided by 2 times h, that is 87183. So for the error, for the true error, so that is equals to true value minus the approximated value divided by true value times 100%. Okay, number 3.77%. And now we will compute for the centered difference of accuracy. Okay, that is equals to negative f of a plus 2 plus 8 times a function of x of I plus 1 k minus 8 times function of x of I minus 1 plus a function of x of I minus 2 divided by 12 multiplied by h. Oh, may mali sa formula ko. Wait natin. Is equals to negative plus 8 times functions of x of I plus 1 minus 8 times plus f of x close parenthesis divided by 12 times each. Okay, this equals to negative 0.9125, and for the true error is equal to 0.9125 minus, so 0 na pala siya kasi equals. So kung mapapansin nyo, mas accurate yung center difference of accuracy, so error is 0. So that is almost equal to the functions of f of x. Okay, so it is a perfect result. Okay, next is example of Richardson extrapolation. So you just delete this. So using Richardson extrapolation. So, ano pa yung okay, so using the same function, estimate the first derivative at x, that is equals to 0.5, employing step sizes of h1 is equals to 0.5 and h2 is equals to 0.25. Then use this equation known as Richardson extrapolation to compute for the approximated value of the f of x prime, f of prime x. Okay, for the first derivative estimates, so it can be computed using the centered differences formula. So for the h1, that is equals to 0.5, so derivative of 0.5 step size h1, so that is equals down to f xi plus 1 plus f of I plus 1. So that is since 0.5 yung step size natin, so 0.5 minus 0.5, that is 0, then 0.5 plus 0.5, that is 1. So ang value ng mga f of x, so ito yon. So x of I plus 1, so ito yung magiging x of I plus 1 nya, that is equals to 0.2 minus f of x of I plus minus 1, so ito yung magiging x of I minus 1 nya, minus 1.2. Okay, then divided by what? 2 times h, which is equals to 0.5. So the value is negative 1, and for the true error, it will give a true error of minus approximate value divided by true value times 100, negative 9.5894 error. And now for the derivative of h2, that is equals to 0.25. So that is equals to, so using this naman, f of I, so 0.25, x is 0.5 minus 0.25, then 0.5 plus 0.25, so ito yung gagamitin natin, x of I plus 1 nya. So we have 0.6 minus x of I minus 1, so ito yon. Okay, then divided by 2 times each of 0.25. Then the value is negative 0.93478, and for the error, we have the true value minus the approximate value divided by true value times 100. So the error is negative 2.4%. Now using the Richardson extrapolation, so this formula, so the derivative that is equals to 4 over third 4 divided by 3 times uh, dh2 h2 natin ay 0.25, so ito yan, minus 1/3 times dh1 negative 1. Okay, that is equals to negative 0.9125, so which is equals to the f of prime x negative 0.9125. So the error would be 0. So again, the answer is near perfect. uh, give us a perfect result. Okay. Okay, so that's all for today, guys. So let's continue this on next video lecture. So see you again next meeting.